Hello guys, so in today's video we'll be going through some preliminaries in commutative algebra. First things first, we'll start with the basic definition of a module. Now first I'll say let my algebraic structure of a ring be any ring which is a non-empty, that's if I have a non-empty set. If I have a non-empty set, say M, now I can say M is said to be a left module. Now, why I'm saying that M is said to be a left module will be further discussed during the definition. Now, I proceed by saying if M is an abelian group, meaning M is commutative. If M is an abelian group under the binary operation, plus, now we can say that such that R is contained in the ring R and small m is contained in the abelian group M. Now there exists a small r dot a small m. Now we can see that what we have here is a left ideal. Now we proceed by putting in a parenthesis, saying that the binary operation, which is the multiplication, is defined on the ring M cross M, which is the Cartesian product, which is mapping into the abelian group M, such that the binary operation, which is multiplication, is mapping into R dot M, which is the left ideal. Now, for M to be a left module, it must satisfy this condition. And the first condition is that R dot A plus B is equal to R dot A plus R dot B for all A comma B is contained in M, comma R is contained in R, where M is our abelian group and R is our ring. Now the second condition goes as follows, that R prime dot R prime prime dot A is equal to R prime dot R prime prime then dot A, where A is coming from our abelian group. Now we have for all R prime comma R prime prime is contained in the ring, and our A, remember our A is coming from the abelian group M. Now we proceed with the third condition by saying R prime plus R prime prime dot A is equal to R prime dot A plus R prime prime dot A. Now for all R prime comma R prime prime is contained in R, which is the ring, and A is contained in the abelian group. And finally, the last condition, which states that 1 dot A is equal to A for all A is coming from the abelian group M, in which we call this a unitary a unitary model. Now, we can now see that we can now definitely call M a left module since we restricted it by having a left ideal on the ring. Now, we continue with the proposition that let M be an R module. Then, for all R contained in R, which is the ring, X is contained in the abelian group, which is M. We have that the subconditions that the zero module of R multiplied by X is equal to the zero module of M. R multiplied by the zero module of M is equal to the zero module of M, and C1, which is negative R multiplied by X, is going to give us minus Rx, and R multiplied by minus X is going to give us negative Rx. And the last condition, which is negative R multiplied by negative X, is going to give us Rx. Now, I also noted here that we should note that the binary operation, which is plus and multiplication, which shows us that we are dealing with a ring, since this is with respect to commutative algebra. Now, we have the Cartesian product mapping into the abelian group M. That is the Cartesian product of the ring and the abelian group is giving us a module M. Now, we proceed with the proof. Now, we say that the proof of A, we say that since the zero module of R plus the zero module of R is equal to the zero module of R, that is, if we add two zero modules of R together, we are going to get another zero module of R. Now, we proceed by saying we have that the zero module of R multiplied by X is equal to, now since we know that one zero module of R is equal to zero module of R plus zero module of R, then we now have multiplied by X. Now, if you look at this very well, you will discover that what we are doing now with respect to the zero module of R is that we are constricting it to look like a left ideal. We are dealing with the zero module of R to look like a left ideal. Now, we proceed by saying that the zero module of R multiplied by X plus the zero module of R multiplied by X, where we know that the zero module of R multiplied by X is equal to M. Now, what it implies is that when we have a zero module of R multiplied by X, if X is coming from the abelian group, we are going to get a zero module of M, because M is an abelian group with respect to the binary operation plus. Now, we proceed again by saying since the zero module of M plus the zero module of M is equal to the zero module of M. Now, we can still follow the same procedure by saying that we have that R multiplied by the zero module of M is equal to R multiplied by the zero module of M plus the zero module of M, which is equal to this R multiplied by the zero module of M plus R multiplied by the zero module of M. Now, we proceed by saying where R multiplied by the zero module of M is equal to the zero module of m. Now we see that thus conditions A and conditions B has been established. Now we proceed on to condition C1. Now to show C1, to show for condition C1, since from our previous statements and conditions, we know that since the zero module of R is equal to R plus negative R, now we obtain that the zero module of M is equal to the zero module of R dot X from our previous statement here. Now we now have that since the zero module of R is equal to R plus negative R, which is acting as the identity of an inverse element. Now we have that R plus negative R multiplied by X is equal to R multiplied by X plus negative R multiplied by X. Now given that negative R multiplied by X is equal to negative Rx, which proves C1. Now we proceed to proving C2. Now we proceed by proving C2, in which we say that X plus negative X is equal to the zero module of M. Thus, we have that R multiplied by X plus negative X is equal to R multiplied by the zero module of M. Hence, R multiplied by in bracket Rx plus the negative of X is equal to R multiplied by X plus R multiplied by negative X, which is equal to the zero module of M. Now, our condition, which has been earlier stated as R dot the zero module of M is equal to the zero module of M. Now, by condition B, in which we've proved before, by condition B, we have that R multiplied by negative X is equal to negative Rx. Thus, C2 is proven to hold. Now, we move on to the last condition. Now finally, to prove D. We know that now negative R multiplied by negative X is equal to negative, that is by removing the negative from the X, which is coming from the abelian group. We have negative R, then X. We now say that it follows that negative, which we remove the negative from the abelian group, the element of the abelian group X, then negative R of x is equal to negative of Rx, we close the bracket, which is equal to, negative and negative annihilate themselves. Now we have Rx and not as, this is standing as a warning, and not as negative R x, which is equal to negative R and negative x. Now this is standing as a warning that we are not to place it like this. We are not to place it like this, that this is how we are allowed to place it as. Now, as required, the proof is now complete. Now we can see that commutative algebra is a very interesting branch in mathematics. If you are very interested in abstract algebra, also more videos will be posted down, so please like, share and subscribe. Thank you.